Good morning, everybody. Let me first remind you of the fact that we are going to be exiled on Wednesday. We will have to move to Philosophenweg 12, to the large lecture hall, because of the Schüler Informationstag. So please don't look for the lecture here on Wednesday. This is exceptional. In a week we are going to be here again. Then I was asked, where are the videos? I changed the format a bit. So now you can see all the videos that I have so far uploaded on the video series. If you click on that, you see that. And I did that because the streaming service of the university has updated a bit and is now more flexible, more comfortable, and I'm using more of the features of it now. So much for that. So the menu for this week, who ordered that? Wait a moment. The menu for this week is that I would like to complete what I wanted to say about flows under specific circumstances, then discuss shock waves, and this will have two parts. First of all, we will need to see why shock waves form in a fluid, and second, what we can conclude from their existence. And then, hopefully, if time permits, there will be time left on Wednesday, Philosophenweg 12, to speak about fluid instabilities, which once you notice them, you see everywhere around yourself, right? In rivers, in the atmosphere, in clouds, in a glass of beer, and so on. All right, so much for the menu. Now, last time the main, or the focus was on Bernoulli's equation. So let me restart with Bernoulli's equation and then say a few words about what we did with it so far. All right. This is where we were. What did Bernoulli's equation say? It said v squared over 2 plus a quantity that we call the specific enthalpy plus phi equals a constant along the flow. And I told you that this is essentially an integral of Euler's equation, because we have integrated, or we have projected Euler's equation on the flow, and then saw that along the flow, the quantity to the left of the equal sign is conserved. And you recognize that this is just the specific energy, right? The energy per unit mass that is conserved here. This is the kinetic energy per unit mass. This is internal energy plus pressure volume work, that's the enthalpy, that's the gravitational potential. So this essentially is one expression of energy conservation. And we use that together with continuity, so together with mass conservation, in order to derive a few things which I think are funny. The first was a very simple example that has nothing to do with astrophysics, just the flow from a faucet. The second has more to do with astrophysics, because in astrophysics you also have jets. We looked at the lava nozzle and recognized that first of all, if a flow is subsonic and goes through a tube that narrows, it speeds up. If it is supersonic, it speeds up if the flow widens. If you therefore construct a nozzle that has the sonic transition exactly at its narrowest cross-section, the flow will keep accelerating, and this is the principle of a lava nozzle. And then we finally had an astrophysical example, which was Bondi accretion, and this is the point where I wanted to restart again. Bondi accretion is the case where you have a mass accreting, that is attracting matter from its surroundings. And for simplicity, we assume that the supply is infinite, right? So it can eat as long as it wants, without changing density and pressure of the surrounding gas. And we wanted to see what kind of flow will establish or can be established around that accreting mass. All right, and we set up Bernoulli's equation for that. We set up Euler's equation, we set up the continuity equation on top of that, and then used both equations to eliminate the change of density, and arrived at an expression that looked like that. Where the symbols meant the following. First of all, we introduced a scaled velocity, which is the velocity of the flow divided by the sound speed of the unperturbed gas, so far away from the accreting matter. Then we introduced the Mach number as the velocity divided by the sound speed. Notice the difference, right? One is the sound speed of the unperturbed distant gas, the other one is the actual local sound speed. All right, that's the Mach number. Then we introduced the ratio alpha as rho over rho zero. That's the density change compared to matter at large distance. We had x equals radius scaled by the Bondi radius. And the Bondi radius is something funny, which reminded of the Schwarzschild radius. It's gm divided by some speed squared, and in our case, of course, that's cs0 squared, that was the Bondi radius. And if you replace the sound speed squared here by the speed of light, you get the Schwarzschild radius, which gives you a horizon. And this is maybe one indication that in some circumstances you can mimic the physics of a system with a horizon by a hydrodynamical system. That's very interesting, but I can't go into any detail now. All right. That was that. Now we had two cases here. This was the adiabatic case, or the polytropic case, right, where we assumed that the gas flow is adiabatic, and therefore has no heat exchange, and that was the isothermal case. So in other words, if heat conduction, if heat transport through the gas is slow, for example, because the density is low, could be one example, then you have no heat exchange, you have an adiabatic flow. Otherwise, if heat transport is efficient, you can have an isothermal flow. All right. So that was where we arrived at this expression here. Are there questions up to this point? Yes.
So you said that we have an infinite supply of mass.
We have what? Yes.
But the question is whether we can neglect it, or we can get the rotation of total mass because we assume it's very good.
I'm not sure I understood your question. So the idea is that you have an infinite distribution of gas with density rho and pressure P, rho zero and pressure P zero, and now you place a mass somewhere into it, and it starts accreting. You wait until a stationary flow has established, and then you let it go. No, we don't. No, we don't, because we have the gravitational potential in there. Okay? What we are neglecting is the gravitational pull of the gas itself. Right? We are assuming that we have a central mass m that is attracting matter from the surroundings. Now, as long as the gas distribution would remain homogeneous, it could not exert a gravitational force. But now, the accretion flow creates a concentration of mass, and the gravity of that we are neglecting. But the central mass is taken into account because we have the gravitational potential there. Sorry? Yes. Yes, we are assuming that the mass of the central mass, that is the mass of the accreting object, that is constant. Which is usually a good approximation, because for stars, for example, you typically have accretion rates from the surroundings on the order of 10 to the minus 4 or smaller solar masses per year. So that the amount of material that they actually accrete is very low. But you might have situations in which you would have to take into account that the mass is also changing while it is eating. And sometimes it happens that it collapses from overweight. Stars are objects that are in some aspects really very similar to humans. All right, do you have further questions? Then let me first of all show a picture. Wait, no. Here we go. All right, so you see three curves here, and they allude to, or they correspond to the three cases that I mentioned last time. You see, this equation tells you how the velocity has to change if you change the radius. So as you go inward or outward, the velocity will have to change, and this equation tells you how. So suppose I come from the outside, I move inward, 1 over x is getting larger and larger. Sometime at one point, we call the critical radius, it will set the right-hand side of this equation to 0. And then at that point, obviously, the left side of the equation will also have to be 0, and it has three chances to achieve that. Either u equals 0, or du equals 0, or m1 equals 1. So it could either stop if u equals 0 at the critical radius. That would be awkward. It could either reach a maximum or a minimum, whatever it may be, so that du equals 0 at the critical radius, or it may turn supersonic at that point. These are the three chances of the left-hand side to become 0 once the right-hand side necessarily drops to 0 at the critical radius. And now you see these three possibilities illustrated here. If you look at the dark red curve, that is the one where the flow has velocity 0 at the critical radius. You can't believe that, because that would mean that at one radius, for example this one, you would have two flow velocities. This cannot be a physically relevant solution. Then the other two remain. You have a blue curve here. This is the one that turns supersonic at the critical radius. And then you have the light red curve here, which reaches a maximum velocity of the flow at the critical radius that then becomes smaller again. So these are the 3 formal possibilities of which 2 may be realized. Okay, and then once you have that, you can solve the system of equations that we had for all relevant parameters. So if this turns 0, you can solve for the critical radius. And now I'm taking the isothermal case just because it's less writing. Right? So if xc equals 1/2 in the isothermal case, sorry, if x becomes xc equals 1/2, then the right-hand side becomes 0. So the critical radius in the isothermal case is 1/2. 1/2 of what? Well, 1/2 of the Bondi radius. Okay, and now we can return to solving the rest of the parameters. For example, we now know that the flow velocity u must be 1 in the isothermal case, because we defined xc such that I'm looking at the case where going through the critical radius leads to the supersonic transition. Then the Mach number must be 1 at the critical radius. Mach number is the fluid velocity divided by the speed of sound. But in the isothermal case, the speed of sound is constant. So then the scaled velocity u in the isothermal case is also equal to 1 at the critical radius. So that must be the case at xc. Okay. Then I'm looking at the Bondi mass accretion rate that we had defined last time, which was the combination of constants 4 pi rb square rho 0 cs0. Remember what that was. This is the mass flow at density rho 0 with the unperturbed speed of sound through the surface 4 pi rb square spanned by the Bondi radius. And then we saw that the actual accretion rate, m dot, equals minus, well, this thing here, times now x squared alpha r. Okay, and now I would have to write down the actual speed of sound, but for the isothermal case, this is the same. So if I now write xc here, then I get the actual accretion rate from the Bondi accretion rate here. And finally, I need the actual density. And this I get from the continuity equation. Right? So in this way, you can calculate the actual flow parameters for the case when the flow goes through the sonic transition at the critical radius. And then if you reduce the accretion rate, you get a flow that remains always subsonic at all radii. Okay, now, what do you think would happen if you reversed the fluid flow? If you said the mass at the center does not accrete matter, but expel matter. For example, you have a star there that is so hot that it drives the wind. Right? O stars, B stars do that. In that case, you would have exactly the same situation, with the only change that the sign of the mass accretion rate would turn. And then you do not get the Bondi accretion solution, but you get the Parker wind solution. But the only change is one change of sign, right? And the rest remains. Okay, that's what I wanted to complete on Bondi accretion from last time. Do you have questions up to this point? If this is not the case, then let me discuss briefly one particular case of viscous flow. And the only reason why I'm doing that is to illustrate how far you get, or how far you can get under situations of specific symmetries if you want to solve the Navier-Stokes equation. So, the situation I have in mind is the following. I'm imagining a long tube, a long cylindrical tube. This is to indicate it's long. It has length L. And now I'm imagining that I apply, I fill the tube with a viscous fluid, with viscosity eta. There will also be a theta, but it won't matter, you will see. And I apply along this pipe, along this tube here, a pressure gradient delta P. In other words, right, you're sitting in a cafe, you have some nice iced coffee or cocktail in front of you, and you want to drink that with a straw. That's the situation. Okay, now, of course, if you are in a situation like this, the first thing you think of is the Navier-Stokes equation, I hope. Right? And now let us have a look at the Navier-Stokes equation. Let me first write it down in full beauty and then we'll see. All right, that's what you think of when you have a cocktail in front of you, I'm sure. Now, how do we apply this equation to the situation in question? So, first of all, I'm assuming that the tube is long enough so that I can study a situation under translational symmetry along the x-axis. In other words, I want to study the flow somewhere deep within the tube. Okay. What does this mean? This means that gradients of something along the x-axis must be zero. I shouldn't write it like that. Wait a moment. This means that gradients, or the derivative of the fluid velocity along the x-axis must be zero. Right? The flow velocity won't change along the tube, and we also have that there is no gradient in the fluid density along the flow. All right. I'm also assuming that somewhere within the tube the velocity only has an x component. Right? There are no y and z components. So v equals let me write it in either way. Either in this way or in that way here. So there are no y and z components of the velocity. Okay. What else? If I have a translationally invariant situation along the x-axis here, then I can write the pressure gradient as simply delta P over L, right? And the pressure gradient must be constant along the flow, along the tube. So therefore, the gradient P is going to be delta P over L. Okay. What else do we want? We have continuity in addition. And now we need to see what all these symmetry requirements mean for the flow. First of all, the flow is supposed to be stationary, so the partial derivatives of rho and v are going to disappear. Then, if I look at the continuity equation here, I know from our conditions here that the vector rho times v only has an x component. So this means that the divergence can be written as dx rho vx equals 0. Now what does this mean? Dx rho times vx plus rho times dx vx equals 0. But the flow velocity along the x-axis does not change. So dx vx equals 0. But since vx is not 0, unless you stop drinking, dx rho must also be 0. We would have guessed this before, right? Okay. So these are these conclusions. Now let us look at what remains of our proud Navier-Stokes equation here. The velocity times the gradient can only be vx times dx. But vy and vz are 0 anyway, and dx vx equals 0. So this is gone by symmetry. This remains, but the gradient of p can be replaced by delta p over L simply. All right, there is no help about that. Here we have the divergence of v, which shrinks to dx vx, because there is no vy and vz. But dx vx is 0, so this whole thing is 0 anyway. Okay, so what remains is the simple equation delta p over L equals eta nabla squared v. All right, but now this Laplacian that remains here cannot have an x contribution, right? Because the derivative of the velocity field in x direction must be 0. So all that remains is here a Laplacian in 2 dimensions, right? A Laplacian in the cross-sectional plane of the tube somewhere along the flow. So this must be a Laplacian in the coordinates y and z only, right? In the coordinates perpendicular to the flow. But then I have a two-dimensional Laplacian, and the cylindrical symmetry of the flow suggests that we introduce cylindrical coordinates. So if I write this in terms of a cylinder radius r, then I can write the Laplacian as that. Right? It's 1 over r dr vx. That's the Laplacian in two dimensions. If you had it in three dimensions, it would be 1 over r squared dr r squared dr in a spherically symmetric situation. Here we have a cylindrically symmetric situation, and we have a two-dimensional Laplacian. All right, so now what do we have? We have an ordinary second-order differential equation for that's correct, yes, for the velocity. And of course, we can directly integrate that. Yeah. There's rho missing, indeed. All right, good. So we are just going to invert this equation by two integrations. Right? The first thing I do is I write this as 1 over r dr vx, and this is delta p over rho L eta. And now we can integrate twice, right? Now I first multiply the equation with r and integrate, such as to remove this. Then on the right-hand side, I have a factor r that I need to integrate over. This will give me an r squared over 2. In other words, I can write r dr vx equals delta p over rho L eta r squared over 2 plus some integration constant, because I do not want to care about boundary conditions right now. Right, so I have to add a constant here. Okay, that's the first integration step. Then I can divide by r and integrate once more. Let me do this right underneath. So now I divide by r. I get an r over 2 here. I have to integrate over r. This turns the r over 2 into r squared over 4. So this means Vx equals delta p rho L eta r squared over 4. Then if I divide by r, I get an a over r. If I integrate this, I get an a ln r plus b. Now that's our general solution for the velocity field Vx. And it's a velocity field now because it depends on the coordinates perpendicular to the flow. In our case, only on r because of the cylindrical symmetry. Now, of course, we want the velocity to remain regular at the center of the flow, so along the central axis of the pipe, of course, right? So if a was anything different from 0, we would get an infinite term here, which we don't want. Right? So we have to set a to 0. And then we want to set the flow velocity to 0 at the boundary of the flow, right? At the rim of the tube. Right? Otherwise, we would have permanent friction between the flow and the tube that would slow down the flow such that its velocity became 0. Right? So we have two boundary conditions. The first is Vx must remain regular at r equals 0, and we want to have Vx equals 0 at r equals capital R. These are our boundary conditions with which we want to solve that equation. The first one tells us that a must be 0, and the second one tells us that b must be minus delta p over rho L eta, all these constants, times r squared over 4. Right? Just has to cancel the first term at the boundary of of the tube. And this gives us the final solution. Vx equals delta P over rho L eta r squared minus r squared divided by 4. So we get a parabolic velocity profile that falls to 0 at the boundary. But now the interesting question is, how much matter do you get through that pipe? In other words, how much can you drink per second if you apply a certain pressure gradient, a certain pressure difference? So what is the amount of matter that you get through that pipe? M dot, right? Well, what is that? That's going to be the matter flow, rho times V, integrated over the entire cross-section of the pipe. So, this is going to be r dr d phi. That's the integral over the cross-section of the pipe. This goes from 0 to capital R, that goes from 0 to 2 pi. Now, rho times V, x. Okay, are the units correct? This is an area. This is grams per cubic centimeter. So taken together with the area, this is grams per centimeter. You multiply this with centimeter per second, and you get grams per second. Right? That's the amount of mass that you can pull through that pipe. Okay, now what is this? This gives a factor of 2 pi from the integration over phi. Rho is supposed to be constant anyway. Then we have all the rest of the constants, delta P, rho L eta. Rho cancels out, lovely. What remains is an integral over r dr, r squared minus r squared divided by 4. And this goes from 0 to capital R. Okay, so this is 2 pi delta P over L times eta. These are the constants out front. Now we have an integral over r cubed divided by 4. This gives me an r to the 4th power. Wait a moment. Okay, yes, well, we could have cancelled the 2 here, but nonetheless. Okay, that gives me an r to the 4th power divided by 16. And then to be evaluated at 0 in capital R, I'm coming to that. And then we have r dr integrated. That gives me an r squared over 2. Together with that, an r squared over 8. And this to be evaluated between 0 and r. Okay. Gives me a factor of capital R to the 4th power in both terms. This one is half of that one. So I get 2 pi delta P over 16 L eta R to the 4th. Or, wait a moment, there's a minus sign. Or minus pi delta P over 8 L eta R to the 4th. Why is there a minus sign? Do you get negative mass from your straw? Did you make a mistake or what? What does the minus sign tell you? Yes? The flow is opposite the pressure gradient, obviously. Very good. Okay, but now you see the flow depends on R to the 4th power. So suppose you drink that cocktail together with somebody else, right? Make sure you get the biggest straw. And if it has twice the radius, it's going to have 16 times the matter flow. Be careful. All right. The result is the so-called Hagen-Poiseuille law. Viscous flow through a pipe depends on the fourth power of the pipe cross-section. It's one of very rare cases where you have a dependence on a fourth power in physics. All right. That's what I wanted to show you, not because of its astrophysical relevance. It doesn't have any as far as I'm aware. But to demonstrate one particular case where you can deal with the Navier-Stokes equations very well. That means the main part of what we have been doing here is to see, okay, you start with this formidable equation here together with the continuity equation, and then you apply symmetry arguments in order to break it down to a really manageable size here. And be sure there will be one problem on a problem sheet where you will be asked exactly to apply that, right? Just to, first of all, not to be scared by the Navier-Stokes equation, which otherwise easily happens, but also to see, okay, if you apply symmetry arguments one by one, you can, in many cases, simply break this down to something that you can solve. All right. And of course, it's quite interesting, right, to see the Hagen-Poiseuille law here. And this interesting dependence on the cross-section of the pipe. Okay. Do you have questions? Yes. No. Rho equals constant is a conclusion from the continuity equation. Okay. Okay. You mean whether we could assume the density to change across the pipe? We could have done that, yeah. We have, in fact, assumed that the density is constant across the floor. Yeah. Okay. This would be a good point to have a break right now, because next thing I wanted to do is to turn to shock waves. And this means that, first of all, we have to understand why shock waves form, and for that we need a new method. The method is called the method of characteristics. It's quite easily explained, but it would be nice to have that after the break. So let us have the break right now and restart, well, just after 10. Okay, let's move on. And as I said, what we are first going to do is to have a look at the so-called method of characteristics. So suppose it's Christmas and you unwrap your presents and you find a differential equation among them like that. And of course you're happy, right, because it's beautiful. And then, first of all, you need to know what are these things? What are these symbols? So this is an equation for, in this case, a two-dimensional solution vector u. And I've limited this to two dimensions just because I want to introduce two variables x and y here, but of course you can extend that if you like. So therefore, x and y are 2 by 2 matrices, and Z is an inhomogeneity that's also a two-dimensional vector here. That may or may not be there, we're going to see that. Okay, now how do you solve that? Suppose there was a vector ds a vector of differentials ds1 and ds2 such that if I multiply this from the left with x, I get a transpose 2 by 2 transpose two-dimensional vector L times dx. And if I multiply the same vector of differentials to the matrix Y from the left, I get LT times dy. Suppose I had such a thing. What would that mean? That would mean I want to change differentials dx and dy to differentials ds1 and ds2. In other words, I want to rotate my coordinate frame. Okay? How? Of course, in such a way that I can solve the equations. But suppose a vector like this would exist. Wouldn't that be nice? Because then I could multiply our initial differential equation by ds transpose from the left and let me just write the scalar product of ds with z as z times ds, right? Which formally would be ds transpose times z, but this is the ordinary meaning of the Euclidean scalar product. Okay, so I multiply the original equation by that. Now, by assumption, ds transpose times x would be L transpose times dx, so this would be dxu dx plus L transpose dyu dy, sorry, okay, equals scalar product z times ds. And now you see dx u dx plus dy u dy is just the total differential of u. So then this would result in L transpose times du equals z times ds. And now I have essentially solved my equation, right? Because then I know that L times u equals z times s plus constant if it has to be. In other words, I'm asking, can I find new coordinate directions, ds1 and ds2, such that I can directly integrate my differential equation along these new coordinates? Okay. So the whole question, or the whole problem, boils down to asking, do I find such a ds1, ds2? Well, let's see. Suppose I multiply this equation by dy and this equation by dx, and then I'm going to subtract both. Then, subtract not both, but one from the other. Let's subtract the second from the first. Then the right-hand side would be gone. On the left-hand side, I would have the same vector ds transposed, and I would multiply this with a matrix which looks very nice, right? The matrix x dy minus y dx. Now, of course, one solution is ds equals 0. Boring. How do I get non-trivial solutions? So solutions different from 0 from this equation, or under which conditions? Linear algebra. When can I find non-trivial solutions of an equation like that? What's the condition for that? Yes? The determinant has to be 0, exactly, right? Otherwise, I could just invert the whole thing, and then ds would have to be 0. So I need to require that the determinant of this expression is 0. Then I know that I can find ds1 and ds2. I'm asking that question because it will reappear in plasma physics and in magnetohydrodynamics over and over again, right? How do you find non-trivial solutions of an equation like that? You search for vanishing determinant here. Okay, so you search for the, yes?
Could you explain really quickly why the transpose factor is dropped when we integrate? Like for the L matrix?
Are you here?
No,
Are you?
Yeah, they're from to the next year.
Okay, because that is just the ordinary scalar product that I write in the usual way. Otherwise, I would have to write it like this, which I understand is the same thing. Okay. So what do? We need to search first whether we can satisfy the condition that this determinant must vanish. Yeah.
Sorry, I meant one step even further where there's the L.
This one? Yes. But again, right, I'm just writing scalar product x times y, which would, according to the rules of matrix multiplication, require a transpose on one of them. Okay? Good. All right, so we search for conditions under which the determinant can vanish. Then we find the vector ds as an eigenvector to the eigenvalue 0 of that matrix. Right? I mean, just by its origin, it appears on the left side of the matrix. But if you want, you take the transpose of that and write the vector ds in an ordinary, as an ordinary column vector. And then you see, okay, ds is an eigenvector of that matrix here to the eigenvalue 0. And then I have my preferred direction in the coordinate plane xy. Right? Then I know into which direction ds and ds1 and ds2 have to point. such that I can directly solve my original equation. All right. From this condition here, you will get a condition on dy dx. And these lines dy dx that arise from here, and you will have two, right, because you have a 2 by 2 matrix here. The lines defined by this differential here are called characteristics of the differential equation. Okay. So you see, what is the procedure? You start with a differential equation like that. Differential equations like that are called quasi-linear because they are linear in the highest derivative appearing. Now here it's almost trivial because the highest derivatives appearing are of first order. So we can set up a matrix equation for the highest order derivatives here. So this is a quasi-linear differential equation. And all we essentially do is try and find directions in the space spanned by the independent variables such that along the characteristics of the differential equation, we can directly solve the differential equation. So we are searching for preferred directions in the xy plane. All right, so much for the method. Now let's apply this to the hydrodynamical case. And then, of course, in the simplest case, we have 3 spatial dimensions and 1 time dimension. These are 4 dimensions, and I don't want that. So I'm artificially reducing the hydrodynamical equations to 1 spatial dimension. So then, what does it look like, or what do they look like? d rho plus dx rho v equals 0. This is continuity now. And dtv plus v times dx times v plus dxp over rho equals 0. I'm leaving out gravity as well. Okay, so this is one thing, right? The method of characteristics. What I'm now driving at is at an application of the method of characteristics to hydrodynamics in a one-dimensional case. Okay. Now I'm going to use the following relations that we already know. I'm going to use cs square equals cs0 square times rho over rho 0 to the power of gamma minus 1. You believe me, do you? I'm also going to use cs square equals gamma p over rho. I think I'm going to use that. Okay. And I'm going to use the relation for the sound speed now to replace, first of all, the density by the sound speed. And I would like to have an equation, 2 equations, not for the density and for the velocity, but for the sound speed and for the velocity. That makes the characteristics much nicer, but you'll see. So I'm going to conclude from there that 2 times dcs divided by cs equals gamma minus 1 d rho over rho. I'm using the same trick as with Bernoulli's equation last time. I'm taking the differential of this equation here, getting 2 times CS dCs on the left-hand side and gamma CS0 square gamma minus 1 and so on the right-hand side. And then I'm going to divide by the original equation. Then I'm getting these relative changes here. Which means that I can replace 2 times dt Cs over Cs equals gamma minus 1 times dt rho over rho, and the same for dx Cs and dx rho. Okay. One more thing is that I'm going to use dxp equals Cs square dx rho, and according to the definition of the sound speed. Okay, now equipped with the relations on the right hand side, I'm going to return here. I'm going to write the first equation, continuity, as dt rho over rho plus dxv plus v dx rho over rho equals 0. Right, what did I do? I just expanded with the product rule this derivative here, and then I divided by rho, the whole equation. Now I'm going to use this relation here in the form dt or x of rho with respect to divided by rho equals 2 times gamma minus 1 dt or x Cs divided by Cs. In other words, I can write this equation as 2 divided by gamma minus 1 dt Cs over Cs plus dxv plus 2v divided by gamma minus 1 dx Cs divided by Cs equals 0. Okay, I'm just gradually, step by step, eliminating all the density dependencies for derivatives of the sound speed. Now I'm going to multiply the whole equation by the sound speed, and then we have 2 divided by gamma minus 1 dt Cs plus Cs dxv plus 2v divided by gamma minus 1 dx Cs equals 0. Okay, this is the unchanged continuity equation, just expressed in terms of the sound speed instead of the density. So we are going to use that as we move on. Now, I'm going to apply the same to the second equation, the Euler equation, where I just copy the first 2 terms, and then I'm inserting this relation here for the sound speed, for the pressure gradient, and get Cs square dx rho over rho. But this is 2 divided by gamma minus 1 dx Cs over Cs equals 0. Now I'm going to cancel one of the Cs factors, and I'm done. So in addition to that equation, I'm going to use dTv plus v times dxv plus 2 Cs over gamma minus 1 dx Cs equals 0. That's the second equation I'm going to deal with, and now I'm going to bring this in matrix form. So I want to have one matrix multiplied with dtCs, dtv. So here's the factor multiplying dtCs. In the first equation, there's no further time derivative. So there is, in particular, no term that contains dtv. In the second equation, I only have dtv, but no dtcs. So these are the time derivative terms in both equations. Now, I want to have the same for the spatial derivatives in the same order, right? dx cs and dxv in one vector. So, the factor multiplying dx cs is 2v divided by gamma minus 1. The factor multiplying dxv is cs in the first equation. The factor multiplying dx cs in the second equation is 2cs over gamma minus 1. The factor multiplying the dxv in the second equation is v. All right, now I have the hydrodynamical equations in matrix form, in the form of a quasi-linear equation. If I introduce as u the vector composed of the two velocities cs and v, and define this first matrix as capital T, the second matrix as capital X, then you see that you can write the hydrodynamical equations as T times dTu plus X times dXu equals 0. So we have them now brought into the form of a quasi-linear differential equation without inhomogeneity z. So in comparison to the general case of a quasi-linear equation, we have a 0 inhomogeneity. Okay, let me summarize. Continuity and Euler together can be brought into this form with T equals, as written down there, 2 divided by gamma minus 1, 0, 0, v. Sorry, no, 1. And X equals 2v divided by gamma minus 1 cs. Then reverse, right? 2 cs divided by gamma minus 1 v. Okay, and now we can apply the entire machinery of searching for the characteristics and so on to these matrices. Now it's just working down a recipe. So what's the first thing we have to do? We have to use the condition determinant of t dx minus x dt equals 0. That was the condition under which we could hope to find differentials ds1 and ds2 such that along the directions of ds1 and ds2 we could solve our equation. Now what is that determinant? Well, this is 2 divided by gamma minus 1 dx minus 2 v dt divided by gamma minus 1 from taking this element, multiplying it with dx, subtracting this element, multiplying with dt, So this is the 1, 1 component of the matrix whose determinant we seek. Next one, 0 times dx, okay, minus cs times dt. 0 times dx minus 2 cs dt divided by gamma minus 1. 1 times dx minus v times dt. Oh. That's the matrix whose determinant we want to be 0. Okay. So this is the determinant of a common prefactor in the first column, 2 divided by gamma minus 1. Now, dx minus v dt, cs dt, minus cs dt. Sorry, there should be a minus sign here as well, because I have to subtract x dt. And now if you have a single column or a single row in a matrix whose determinant you want to find, which have the same prefactor, then you can just pull this prefactor out, right? Because then every term in the determinant will be multiplied by that. So I can write this as 2 divided by gamma minus 1, determinant of dx minus v dt minus cs dt minus cs dt dx minus v dt. Okay? Good. Now the determinant is easily calculated. So this requires then that dx minus v dt square minus cs dt square equals 0, right? Because then the entire determinant is going to vanish. And this means that dx square minus 2 times v dx dt, now plus v square dt square minus cs square dt square, so plus v square minus cs square dt square equals 0. Now we have a quadratic equation for dx as a function of dt. We could likewise solve for dt, wouldn't matter, nonetheless. So we get dx plus or minus. We are going to get 2 characteristics. No wonder we had a 2-dimensional equation. It's just the solution of that, so that's 1 over 2 times 2v dt plus or minus square root 4v square dt square minus 4 times v square minus cs square dt square. That's the solution of that quadratic equation. Now you see that's pretty easy. The 4v squared drops out. Under the square root, we just retain 4 times cs squared dt square. And if I pull everything together, I get dx plus or minus equals v plus or minus cs dt. These are the characteristics of our hydrodynamical equations. What do they say? They have a very, very intuitive physical meaning. They tell you that the characteristics follow from integrating this equation here, and these just give you the sound cones, the Mach cones, right? You have one branch of the characteristic propagating with v plus cs. So if you set the sound velocity to 0 because you swim with the flow, then the characteristics would just follow plus cs, right? That's a sound signal traveling to the right. Equally, you could have a sound signal traveling to the left. So the characteristics turn out to be the Mach cones of the sound waves in the fluid. Ernst Mach, you know him, right? Mach Sachen and so on. Okay, now we have the characteristics, now we can walk our way back, right? Because now we can specialize this matrix here along the characteristics and ask what are the components of the vector ds such that ds is an eigenvector of that matrix with eigenvalue 0. So I want to have t dx minus x dt, okay? So just the same matrix. All right. So ds1, ds2 multiplied with this matrix must be 0. Right? 0 times ds1, ds2 such that ds1, ds2 is an eigenvector of that matrix with eigenvalue 0. All right, now I could multiply this vector here, this row vector here with this column vector, or I could multiply it with this column vector. Both must be 0. Both will give me the same condition. Of course, multiplying it with the second column vector here is much easier, so I'm going to do that. So this leads to minus cs dt ds1 plus dx minus vdt ds2 equals 0. In other words, somehow I now have to take the characteristics into account. So let me replace the dx by dx plus or minus, which would be v plus cs times dt. And I'm going to make this replacement now. Then you see the v dt goes away, and I retain minus cs dt ds1. All that remains is now plus or minus cs dt. Okay, from which you see that ds2 must be plus or minus ds1. Now we have our preferred directions. They are just diagonals, right? The diagonal lines. Okay. Now we need to go one more step back, namely we have to identify the vector L. So again, right, we are using the method of characteristics. We have identified first under which conditions the determinant of this coefficient matrix vanishes. Now, we went this step back and asked, what does the vector ds1, ds2 have to look like, such that it is an eigenvector of that matrix with eigenvalue 0. Now we know by construction that this is possible here, right? That there exists a coordinate differential ds such that one of these relations is true. Okay, so now we can use either of these relations here in order to find the vector L. All right. So now we know that, and we know that. Now we need to use ds1, ds2 multiplied with, for example, the matrix T, which is the simpler one, must be vector L times dx. So that is L1 dx, L2 dx. This is now our equation for the vector components L1 and L2. And we know that ds2 is plus or minus ds1. Okay, so what do we get from that? We multiply this with the first column. This gives you 2 ds1 divided by gamma 1 equals L1 dx. Multiplying this with the second column vector just gives us plus or minus ds1 equals L2 dx. And this doesn't fix the vector L completely, because you can still give it an arbitrary length, but it sets the ratio L1 divided by L2 to plus or minus 2 divided by gamma minus 1. Now you could, for instance, set arbitrarily L2 to 1 and say, okay, my vector L looks like plus or minus 2 divided by gamma minus 1. Like that. Okay? That's the vector L now. And now finally, I know that L times U is CSV equals Z times ds, but Z was 0. So this is just a constant here. And I call these constants capital R plus or minus. Okay? So let me return to the method of characteristics to show where we are. Again, this was the condition for us to find a preferred direction in our coordinate plane. We found it. Given these directions are given by the characteristics describe the Mach cones. Then we use this equation here to actually find the coordinate differential ds1, ds2. This means it exists. This shows you what it is. This equation tells you, or that equally, what the vector L has to be like. That then tells you what the solutions must be like. In our case, in the hydrodynamical case, the right-hand side, so the inhomogeneity of the equation was 0. So we can just conclude that L times U must be a constant. So we see that this condition must hold. So from here we get V plus or minus 2 times Cs divided by gamma minus 1 equals R plus or minus. This is a most remarkable result. It tells you that, clearly restricted to our one-dimensional fluid flow, but these quantities here, V plus or minus 2 Cs divided by gamma minus 1, are constant along the plus or minus characteristics. Right? So if you set up the Mach cone, the characteristics of the fluid, then you know that along the plus characteristic R plus and along the minus characteristic R minus will be constant. These are called the Riemann invariants. All right, and now we have a really very powerful tool that allows us to see how fluid flows are going to move. Let me briefly sketch what we are going to use this for next time. And then we come to a conclusion. So the situation I now want to consider is that you have an unperturbed fluid or an unperturbed gas. And not enough color. Yes, we do. Okay. So here's the x-axis now. And here's the time axis. I want to deliberately allude to to special relativity, right, to a space-time diagram. But this means now that since we have expressed our characteristics as dx dt, I now need to take into account that what I'm showing is dt dx. Okay? This is just to make the similarity. Okay. Now I'm assuming that I have unperturbed fluid up to time t equals 0. And then at time t equals 0, let me just do it like that. At x equals 0, I want to make some noise. And I perturb the fluid in some way. Now I know here the sound speed is cs0, for example. And the velocity is also 0 because the fluid is supposed to be unperturbed. No, cs0 is constant. And we have v equals 0. All right. Now I can connect any point along the x-axis here with a minus characteristic here to some point in the unperturbed fluid. And I know that along this minus characteristic, the Riemann invariant R minus will be constant. In other words, this tells me that V minus 2 times Cs divided by gamma minus 1 equals R minus equals constant along the entire line here. But of course I can relate it to this point here, which will have velocity 0 and sound speed Cs 0. So that will be minus 2 Cs 0 divided by gamma minus 1. In other words, these characteristics now allow me to draw conclusions throughout the fluid, to relate fluid points to each other, and to use that along these characteristics, the Riemann invariance will be conserved. So this will tell me that V equals 2 gamma minus 1 Cs minus Cs 0. In other words, right, if I now perturb, for example, the fluid velocity here in some way, the fluid density here in some way, I will also perturb the sound speed. And then, according to that, the fluid will have to move. And it tells you how it's going to move. Now, how does it move? And this is the really decisive point now. As I increase the density, the sound speed will also increase. Okay? So if I imprint a density perturbation here, which is very dense here and less dense here and less dense here, it will move the faster the higher the sound speed is, or the higher the density is. So if you now look at a perturbation like this, right? This part will move slowly, this part will move faster, this part will move faster, this part will move even faster. What will happen to the wave? The denser parts will crash into the less dense parts, necessarily. Okay? This is why shock waves have to form. Because the sound speed increases with the density and therefore waves become unstable. Right? Denser parts of waves move faster. That's the point. And without solving the hydrodynamical equations for a certain situation, we see this directly from the Riemann invariance here, and so from the constants that we have identified on the plus or minus characteristics of the flow. Okay, that's the key point, right? If you forget all of the derivation, right, the method of characteristics, the application to the hydrodynamical equations, this is the key point, right? Sound waves move, or matter in sound waves move faster the denser the region is that it moves through. And this is why sound waves deepen up, because faster parts or denser parts of the wave run into less dense parts. So ultimately, if you let this go for a while, this will develop to a density profile like that. Okay? That's the key point. Now we could try and create a shock wave here, but for this I would have to shout so much that I'd rather not try. Wednesday, we then look at, so now you know why shock waves form. On Wednesday, we will look into conditions that we can, or about conclusions that we can draw on shock waves without knowing anything more than certain quantities have to be conserved across them. All right, this will lead us to the Rankine-Hugoniot shock jump conditions. And then we see how far we get. Wednesday, large lecture hall, Philosophenweg 12. Don't forget. I'll send a message. Don't get annoyed. Nonetheless, we see each other over there. And unfortunately, the probability is high that I will go here on Wednesday, just forgetting that and so on. So if you don't find me over there, you know why. All right, see you on Wednesday then.